I'm not sure about the video, but the okay, well, thanks much for coming. Really happy to see you. I'm not sure if the video recording will be here. Maybe if there is no touchpad, so maybe we may want to keep another room for Thursday so that we will be more interactive. So, oh, by the way, there are some not literally the same, but impossible books. I brought this one and another one which is not here. Just pass around how the books look like on this subject. And we last time we were done with philosophy of computational chemistry and molecular Hamiltonian, and the goal for today's meeting is, of course, we will refresh what was considered last time, and we need to realize main challenge and pave the way to resolve it. The main, I'll summarize it right now, there will be no intrigue. Main challenge is that number of independent degrees of freedom is impossible to solve by any of today's computers. So one needs to divide and conquer, to simplify equations in such a way that amount of independent degrees of freedom will be under the availability of today's computation. So last time we looked through the skills that we are intending to get through the course, and it will be like basically electronic structure, some reaction dynamics or reaction barriers with additions for like dynamics and optical properties, also with visualization. And here is the summary of the course. So in the labs on Wednesday, we'll run correct software on correct hardware, and basically this course is putting in molecular models and getting some of their observables. So this is most interesting, and maybe most interesting thing is when you implement it and present to your colleagues and get credit for it, papers. But in the most of the time that we spend in lectures, we will focus on this part. Do not develop too much laughter, because you all know this equation. It's only a symbol. We will look on few more. Right? So there are theory backgrounds that help us to develop software that is implemented and helps to predict properties of materials and molecules.
So which part are we focusing on mostly in this class?
The theory behind the modeling of materials.
Okay.
It's the grading and final projects will be based on the skills, but objectively, skills are not too complicated. If we all want just to be well-trained lab technicians, we can look only on skills and complete everything like in 3-4 weeks. But then we will not be competitive researchers, and it will be more difficult to publish or to plan research in the future. So these background theories for practical computations are really needed, even at a small introductory level. So a molecule is a set of positively charged nuclei and negatively charged electrons, and if we need to set up a model of a molecule, we need to record positions of each ions, each of the electrons, and if we accept the idea of micro objects, electrons are quantized, one needs to process the model of each molecule with quantum equations, primarily Schrodinger equation. So if we need to deal with Schrodinger equation, we need to accept an idea of wave function, which is square root of probability distributed in space. We need to accept the concept of the operators for each observables, which are often differential operators. And we need to accept the concept of Hamiltonian, which is summation of kinetic and potential energy, right? And if we do know the solution of the time independent Schrodinger equation, they can be used as a, so the solutions eigenfunctions, and I'm skipping the argument, which is position, and eigenenergies can be used, and here is the H bar, which was hidden last time, can be used to compose time dependent. So one can go to the next step and predict the change of electronic properties with time. And here are different here is most important thing, most important figure from last time. These ugly arrows and circles is a molecule of molecular hydrogen. Okay? So if you need to quantify input parameters for describing any molecule, for example, molecular hydrogen, you need to set up origin, put vector positions of ions, first and second, and then the vectors for positions of elements. These vector positions are needed. Why are they needed? Huh?
What did you say?
Why we need positions when we need positions of all of ions and electrons? What are we going to do with them? Of course, we are not going to do anything. Everything will be done by a computer, but we need to get an idea what is being done there.
Defining the differences in terms of
Yes, differences. And why do we need differences?
we used it to calculate the potential.
Yes, to plug it into Coulomb's law for either attraction or repulsion. So yes, you were right. If we know positions, we can find differences, and there are like 6 of them. I can graphically draw them. I'll probably entertain you with a little homework for the weekend when taking slightly bigger molecule and you count number of terms for kinetic and potential energy. But it should be like a little upscale kindergarten. We all will complete it. Like maybe 4 or 3 nuclei and 3 electrons.
Do you want to leave this?
Okay, leave it somewhere. So the Hamiltonian consists of which types of energy? Yes. So for potential energy, we use Coulomb's law, and in atomic units we skip any factors, so it is just difference in the denominator. So if we carefully subtract all these vectors, and then we will see that for Coulombic interaction, there are always 3 types of potential energy, right? So if you take different molecule, the number of terms will be different, but types will be the same. So N capital, nuclear to nuclear repulsion is positive because they are of the same sign. Electron repulsion also positive factor and difference of lowercase r for electrons, and then n capital E lowercase electron to nuclear attraction, right? So electrons like to be near nuclei. It's not a surprise. Good. And for kinetic energy, you have just momentum squared. Good. So when you add all of them together, it will be the molecular Hamiltonian. And if you have Hamiltonian, you plug it into Schrodinger equation. If it is molecular Hamiltonian, it will be molecular Schrodinger equation, right? We are about done with recalling what was done last time. So 2 terms for kinetic, nuclear kinetic energy, electronic kinetic energy, and 3 terms for potential energy. So this is very ugly equation that is not possible to solve today, even for very small molecules. Maybe with advent of quantum computers, some people will solve them, but today it is unsolvable. For example, if we consider benzene molecule, how many nuclear degrees of freedom are there? Benzene is a chemical molecule, if you're in physics, or if you're not in chemistry, with 6 carbons and 6 hydrogens. Each nuclei has 3 Cartesian projections. So you need 6 plus 6, 12, times 3. Good. Last year I did error and no, 36, yes. 36. So, and it is not the whole story. All Cartesian projections of both electronic and nuclear degrees of freedom are argument of our unknown wave function that we want to find. So we're not going to do it today or tomorrow or anytime. But we need to realize that it is really impossible task. So how many electronic degrees of freedom are there? So hydrogen has 1 electron. Carbon has how many? 6? Sounds right. 1s2, 2s2, 2p2, right? 6. So 6 electrons for each carbon times 6 carbons. 36 plus 6 electrons from hydrogen. How many? And times 3. 126. And plus previous result 36. Something like 160, huh? Yep. So it is just number of independent variables in the unknown function. Typically, we deal with 1 unknown variable, sometimes 3 independent variables for like electricity solving Laplace equation, or right. So we are not going to develop any computer codes, and even if there is a way to solve this equation, we do not have any storage to save this data. So if we numerically represent each degree of freedom with 10 grid points, then we need 10 to the power 150 something bytes to save this information, only for one wave function. And you know the Schrodinger equation has multiple solutions, so several wave functions will satisfy it. So even benzene molecule is not possible to solve. Course is done. Problem is not solvable. What should we do? Yes, we should do like ancient Romans, divide and conquer. So Who ever took partial differential equations? Perfect. So not regular, not ordinary differential equations, but partial differential equations. Huh?
We learned parts of it at the.
Okay. So if you have multidimensional, if it is a, if unknown function depends on more than one variable. What's the most typical trick that you practice? Huh?
Consider the solution and then vector equation.
It's very general for any differential equation. But
Separation of variables.
yes, perfect. So separation of variables. What is it?
Consider one parameter variable and others constant.
It's not wrong, but I would say it slightly different way.
Okay.
Please.
Yeah. So say you have an equation like the Schrodinger equation, and then you have a variable like the wave function that you're trying to solve for. So what you do is that you take that wave function and you make it a product of two other equations, and then you plug that in, plug those solutions into the Schrodinger equation, and then you basically solve for what those like two equations are.
Perfect. Is it? Did everyone hear?
No.
Okay.
I heard, but I didn't.
Huh?
I heard, but I didn't understand. Like I kind of walk.
I will try to repeat and explain, but I cannot say it better. You did a really good job. So, if we have function of several variables, it immediately means example. Abstract things are boring. Let's do practical. Two variables. If we are doing numerical things, we represent dependence on like each variable, just grid points, like data points in table. If there are only 10 grid points, then for one-dimensional function we have 10 points, 10 arguments, and 10 functions. Another function, also 10 points, 10 data points, total 20. Now, if they are two-dimensional, we need to scan both independently, and it will be 100 data points if it is the same resolution, which much more information. So it is 10 times 2. And if you have 2, 3, 4, 5 independent variables, it will be powers. So it will ramp up really quick. So if we can reduce back from function of independent variables to product of independent functions, it will be a real candy, piece of cake. So the idea that Kevin brought in is separation of variables. Represent function where we have a list of variables like psi of x and y as a product of two little psi functions, first function of x and second of y. It's not always possible, but if it is possible, then things become much better. Yeah. So it's not notation, it's going from, if we have 10 grid points, from 100 grid points total to 20 grid points total, if this is possible. What are conditions for separation of variables? When it is possible?
When your wave function is the function of more than one variable.
But it is not, sometimes sometimes it is not possible mathematically. There should be additional conditions that would permit to do it or not to do it. So if the solution is product of independent functions, then differential operator that drives equation should be a summation of independent differential operators acting on each variable separately. It should be summation. So there are mathematical criteria that allow to do the separation of variables. Rigorously, for this problem, it is not possible. But if something is forbidden but we really want it, we'll do it anyway. So there will be some limitations and some penalty for doing it. So we will just estimate how big is the penalty. And you do have an idea what will be our x and y?
back entry? No? Or wait, no, our positions. Our positions.
Positions.
Good lord.
But,
Yeah.
so positions of what?
It in our atoms, our system.
So we have ions and electrons.
Mhm.
So the first goal that would make our life substantially easier if you can separate electronic and nuclear degrees of freedom. If X will stand for all positions of electrons and Y will stand for all positions of nuclei. Then instead of 162 independent variables for benzene, we will have just 36 and 124, each of which is much simpler. And then we'll continue simplifying. You see? So in some sense, what the background for computational chemistry, and do not worry, we will come to practical things very soon. The background for the theories is set of approximations or set of tricks how one can get rid of extra degrees of freedom, or how one can make separation of variables. Because it is not truly mathematical challenge. It's a challenge for practical computations because number of degrees of freedom is untractable, and one needs to make some tricks. If you were taking some level of quantum theory, you may have. No, you do not need to take anything. So here is just shorthand notation. If our wave function does depend on R capital, which can be more than one, interatomic distances, positions of ions, and lowercase r, positions of electrons, then we do want to represent our molecular wave function as a product of electronic part and nuclear part.
You're saying you want this?
I want this, and I will do it, but rigorously, it's not right.
Well, that's just because we're saying we're going to approximate this as best we can approximate this, or you're saying we can't even do this?
We will. It is not rigorously correct.
Yep. Okay.
But we can do it and then estimate how much of precision we will lose.
Okay.
Like if we predict color of molecule, will it be green instead of red because of this approximation, or it will even be moving the gap from infrared to UV or something like this. Okay. And I may not follow my own notations, but whenever I remember myself, I will try to use phi for electronic, theta for nuclear wave function, and R capital for positions of nucleus, and lowercase for electrons. So, what is the criterion for separation of variables? To be able to separate variables in a legitimate way. In case let's not be very general, let's look very narrow-minded on the Schrodinger equation. So Hamiltonian acting on a wave function of multivariables. If the Hamiltonian will be a set of, if it will be a summation of differential operators acting on each variable independently, like derivative over x, or whatever, x1, or second derivative over x1, plus second derivative over x2, plus second derivative over x3, it will be perfect. It will be separable. But if it will have terms like derivative over x1 times derivative over x2, then variables may not be separable. So we need to look if our molecular Hamiltonian includes any cross terms that mix independent variables of different nature. What do you see there on the screen?
Yeah.
There is a bad guy. There is a term that explicitly mix the electronic and nuclear degrees of freedom. So if we if we assume that there is a universe where electrons and nuclei do not attract to each other, right? Maybe it will be not electrons will not stay near atoms and everything will decompose, but so it will be not a very practical universe. But from a mathematical point of view, one could separate variables, right? So in a universe without Coulomb attraction between positive and negative charges, separation of variables will be legitimate. And we can immediately simplify molecular Schrodinger equation. I'm not sure that molecules would exist in such a universe, but it's not my problem right now. So we need to neglect this term and later on bring in how much of correction it delivers back to the solution. So you do have handouts. If you came here not for learning heavy things, but just for entertainment, you may just read biography, right? So the trick of more or less legitimate separation of nuclear and electronic degrees of freedom was done by this two gentlemen. And when you ever visit a place where nuclear bomb was first made, Los Alamos, one of the, it's really small, we are on record. Like big city with 10,000 population, and one of the major cities is named after Oppenheimer because of his role both for nuclear bomb and for Born Oppenheimer separation of nuclear and electronic degrees of freedom. So I will try to compose and entertain you with a very little homework next on Thursday, so that you do it over weekend. And the homework will include counting number of terms, and second, it will be super hard task to go online and find Wikipedia article on Born Oppenheimer separation, something like this. So if you are planning, or if you're already doing, if you're running existing software packages for computational chemistry or electronic structure, you are obeying so-called Born Oppenheimer approximation, which means you are considering electronic and nuclear degrees of freedom as almost independent. If you do not want to believe them, if you want to return electronic and nuclear degrees of freedom in direction, then you need to write your own code or ask someone who wrote it. But among the public and commercial codes, there are no codes that go beyond Born Oppenheimer. So it's not a bad thing. It is a standard thing. If you need just structure, property relations, it could be sufficient. Oh, those are a couple of projects from the first time this class was offered. I wrote it mostly for myself, but you can, if you were relaxing and reading back and taking a nap, now it's time to wait. It will not take a lot of your energy. There will be just one slide. There's very trivial information that I'm sure you all know. Just it is important in the context of this course that you made your focus on. Ready? So electrons are much lighter than nuclei. Right? How many times? Electron is lighter than a proton, approximately. Huh? One more order of magnitude? 2,000 times? So it's like 1,837, but 2,000 times is a good estimate. Since they are so much heavier, the electrons move so much quicker than nuclei. How do we interpret it? What does it mean? If so, it's like, I don't know, binding insects around an elephant. If elephant makes a little step, these binding insects will quickly readjust to new position of an elephant. Right? So the velocity of electrons is so much quicker than the velocity or momentum of nuclei, so that they respond. Of course, they interact, but they, due to attraction between nucleus and electrons clouds distribution change according to follow change in the position of nucleus instantaneously if we take point of view of an elephant of nuclear degrees of freedom. And this is main idea behind Born-Oppenheimer approximation. So if we do want to know shapes of electronic clouds, if you need to solve dependence for electronic degrees of freedom, we can temporarily, as an approximation, assume that nuclei are point charges that being nailed down and do not move at all. This is not correct. This is approximation, but it is a very good approximation. The heavier the nuclei, the better this approximation. So it's not too perfect for proton. Proton has some quantum features, but if you take like lanthanum or uranium, it is not much quantum in its position. There are like nuclear physics stuff inside, but as a position, as a point charge, it's fine. Good. So if your human abilities are on the limit, you may lean back and relax further. You already got the main idea. Yes?
Are you saying like MI and PI? Because I assume that's saying like mass of something is greater than mass of electron.
I stands for nuclei. It's not iodine, and it's not I like a person. It's index, I, J, K. So if you have several ions, we will label them with uppercase Latin indices.
I thought the I meant ion.
No. It's for like summation over I, where I goes from 1 to 12 if it is benzene, or from 1 to 2 if it is molecular hydrogen. Make sense?
Okay, so I stands for the nucleus of each separate atom added together.
I stands for counting index.
Okay.
So atom 1, atom 2, right?
Yes. Yeah, in some sense, they are ions, but if we treat electrons separate of them, they are completely ionized ions, right? If you treat electrons and nucleus separately, it means like we ionized carbon 6 times, 6 plus ion. So it's safer to say nucleus. And the plan is, you don't need to listen. We already discussed most important. I know it sounds like a joke. I tried it in several classes. When you start telling do not listen, people start listening more carefully. So first we will freeze nucleus and set up equations for electronic degrees of freedom. And then we will take solutions for electronic degrees of freedom, plug them into bigger molecular Schrodinger equation, and from there we will develop equation for nuclear wave functions. Okay? So it is the plan. Yeah, important information is done. So, how many types of terms we have in Hamiltonian? Same as fingers on one palm. Yes. 2 kinetic and 3 electronic. 3 potential, right? 2 kinetic and 3 potential. And remember, before, before we had TTVV. Now we have TVTVV. We have regrouped them, and there is a big sign behind it. So compared to previous time when you see this molecular Hamiltonian, it was first kinetic for nucleus, kinetic for electrons, and then all three potential energies. Now we group together everything that relates to nucleus and everything that relates to electrons, and then the bad guy. Right? So the discovery of main point of Born and Oppenheimer was to assign this electron to nuclear interaction as part of electronic degrees of freedom. So assume that this bad guy belongs to electronic degree of freedom and that nucleus moved slowly. And then, so these three terms will be considered as one thing. So the plan is that first we take partial Hamiltonian of these three terms, find solutions only for those variables that are being changed by this operator, and later on we will reconstruct molecular Hamiltonian where these three terms will be as like an addition. But since we will already know the solution for these three terms, the final solution of overall molecular Hamiltonian will be Schrodinger equation will be easier. Binding insects and elephant. Right? Electrons are like biting insects. Elephant is like something that doesn't move from the point of view of a fly. So the three terms that we combine together, kinetic energy of electrons, potential energy of electron repulsion, and electron to nuclear attraction will be treated in the way that positions and momenta of electrons will be treated as true independent variables for which we will solve. And the position of nucleus will be considered as a parameter. If you are comfortable with this, you're so bright. I was resisting this idea until my second postdoctoral term.
How do we relate this back to the equation that we just
So we merge together this and this. Kinetic energy of electrons depends on momentum, phi lowercase. Electron repulsion depends on r lowercase, positions of electrons. Okay? But since we take into account this v sub ne, it will take also the uppercase r, positions of nucleus. But we will try to solve Schrodinger equation for this blue operator, assuming that r capital is not an independent variable. It is a parameter that we set, and for each value of this parameter, we resolve the equation once again. So there will be no differential operator that acts on this r. We will not look for solve in a sense of practice of differential equations for it. It's just parameters that we set up and solve. Okay? Okay, so if we do want to solve Schrodinger equation for this Hamiltonian that includes 3 terms. We will formulate the unknown wave function and unknown energy. The wave function includes independent variables are lowercase and parametric variables are uppercase. The energy, see, it doesn't depend on lowercase, it depends only on our uppercase, because for each value of nuclear positions, for each step of elephant, we resolve this wave function of flies.
R is the elephant and little r is the hands.
Yes.
Yeah.
By the way, who never heard the word potential energy surface? Okay, who has heard it more than once? Potential energy surface. In fact, it is this stuff. So if we, well, one more thing. When we solve Schrodinger equation, we get more than one solution, right? As for typical for differential equations. And this A will be index of the solutions. When we take A equals 1 for lowest possible energy, it will be ground state. Right? And this ground state energy will come up as solution of the Schrodinger equation with slightly different values for each positions of nuclei. If you manually change interatomic positions and resolve Schrodinger equation for electrons, total energy for ground state will be slightly different. And basically, it will reconstruct interatomic interactions with taking into account influence of electrons. So it is what is defined as potential energy surface. We will come through this thing once again. It's just, I was trying to make connection to something pleasant and familiar. Okay. So what is the goal? Solution of the, let's suppose that this quasi-electronic Schrodinger equation can be solved. We know, we do some sort of recursion. We know that it still has a lot of degrees of freedom, but we cannot solve everything at once. Let's assume that this has been done, and we know the solutions, that we know this psi sub A and this E sub A for each position of nucleus. But we do not know yet the nuclear wave functions. Which positions of nucleus are more probable and which are less probable. And our goal is to draw a protocol how to solve molecular Schrodinger equation in general. We know that it is not possible with absolute precision, but at least approximately. So if we do know solution of electronic part, how do we find solution of the nuclear part? Or how we find solution of overall Schrodinger equation where with psi capital depending on both electronic and nuclear degrees of freedom? So, what's your name? Yes. Victor? So you are giving suggestions how to solve differential equations. No? How to solve differential equations. Mm-hmm. So one of the ways to solve differential equations is to make connection between general and partial solutions. If there are several functions that are solutions of a given equation, that their summation will be also a solution, right? If it is a linear differential equation, right?
Yeah, you're bringing back old memories. Yes.
Ah, good.
Yes.
First time I learned about it was 1992.
I was even more.
So I have more rights to forget about it. So why don't we try the trick in this sense? We will take solutions for electronic degrees of freedom, add them together, compose a superposition, and then plug the superposition into overall molecular Schrodinger equation. Okay? And then we will take solutions for different values of parameter that corresponds to position of nuclides. And we take the unknown coefficients in front of these solutions, functions of positions of nuclides. Should I repeat this?
The constants are functions.
Huh?
You said those constants are functions of.
They will be not constant.
Yeah.
These coefficients will
Perfect.
be dependent on nuclear positions. So we will make superposition with not constant coefficients. Okay, let's try. Okay, so here are these phi sub a solutions of electronic Schrodinger equation. Okay. Here will be solution for overall molecular Schrodinger equation. So summation over the solutions A. In which proportions we will add together these known solutions? In the proportions that will depend on positions of nuclides.
So that's an X right after the summation, right?
I don't know how to pronounce it because I'm not Greek.
Oh, it's a Greek.
It's Greek letter that looks like X.
Okay.
Chi, ki. Okay, I will ask your help when it will be time to pronounce it.
What's
Chi.
after the R1?
My perfect calligraphy.
Okay.
Where should I look?
After the red R1, what is? No, it's down. Yeah. Wait, is that an X?
No, multiply.
Well, okay.
Star.
Okay.
So summation, it means that we add together. So we add together phi sub a, and the coefficients in front of this phi sub a will be this Greek letter, and it will depend on the positions of nuclei. So we are making this construction in order to show our loyalty to rules of solving differential equations. Okay? So if summation of general solutions will be a partial solution. So if we plug in this general form into overall molecular Schrodinger equation, it will become an equation for chi functions because phi functions are already known. We should be so happy that we are not doing actual pen and paper solutions, that computers will do it for us.
So chi sub a is the coefficients of our new wave functions p sub a, rho sub a.
Phi sub a, yes.
Okay, so instead of c sub a, we're using chi sub a.
Yes.
Okay.
So the phi sub a depends, it's electronic wave function that parametrically depends on positions of nucleus. The chi sub a, it serves two roles. on one hand, when we just obedient, loyal followers of rules to solve differential equations, it's just coefficient in front of general solution to construct partial solution. But when we are looking on it as scientists, we will immediately discover that chi sub A will be a wave function of quantized nuclei. So when we will solve it for the ground state, it will be like Gaussian in around the centered position where nuclei should be. Like if you have quantized feature of nuclear motions, distribution that ion is not steadily nailed down to some position, but it has some probability to move to left or right, this chi function will illustrate this feature.
So instead of a one-dimensional constant C sub n as we did in like 1 dimensions, now in 3 dimensions, and we're looking at multiple atoms. We're using like chi sub A, and that'll be a 3-dimensional wave function.
Everything what you're telling is correct. This one correction. Letter I, which is not I like a person, not I like iron, not I like iodine. It's an index. And this curly brackets, it means like it goes from R sub I equals 1, I equals 2, I equals 3, so as many atom nuclei as many ions is in our molecule.
So would you have another summation sign supposed to be to the left of the A, and then you have like I?
No.
I understand you're saying it's an index. I get what
it is an index, but it is independent variable. Let me. I have an idea.
So you have to clarify what numbers it's representing. Like just.
Yes. So chi sub A of curved bracket R I curved bracket. So it means that is chi sub A of R I equals 1, comma, R I equals 2, comma. So many R I equals n, where n equals number of ions, of nucleus. Oh.
Yeah, so my question would be, so the equation you're showing us, would you take each individual R, let's just say sub 1, that's going to be its own equation, then you have to take that R, one whole equation, then R2, or you're saying we're going to take chi A, parentheses R1 times R2 times R whatever, so on and so forth, and clarify it at the end.
So right now, we are doing it slowly but surely, one thing at a time.
Okay.
We are not separating this function of many variables as a product, as a function of nuclei number 1, nuclei number 2, nuclei number 3. We still consider that it is a nuclear wave function that depends on all nuclears in the nucleus in the nuclei in the molecule. It's still multidimensional function. If it is a benzene, then this n capital will run up to 12.
Yeah, are you saying that chi sub A is just a function of all the R's?
Yes,
Okay.
yes,
Okay.
yes.
Of all the wave functions.
So it's not 3-dimensional, but for benzene it is 12 times 3, 36-dimensional. Okay?
Mm-hmm.
So we will simplify things. They will be solvable and much easier. But right now we are trying to get a little flavor of how complicated everything is, and we are going through steps how we simplify it too. Yes?
I have a hard time reading here. N is the number of nuclei, right?
N capital is number of nuclei.
Okay, thank you.
Is it a nicely written calligraphy that is easy to read? When I was trying to lecturing for the first time in my life, there were questions like, why your handwriting is so bad? And I said, so that no one catches my errors in English. Okay. Okay. And here's the same thing, just written maybe typed instead of handwriting. Summation of all eigenstates of electronic Schrodinger equation is this chi sub a, depending. So curly brackets means set of all available nuclear degrees of freedom. And this chi sub a is at the same time expansion coefficient and nuclear wave function. So I do not remember how many slides we have left, but I have a feeling that not very many. We are coming to logical completion for this meeting very soon. So the plan is then we need to plug in this functional form into molecular Schrodinger equation, analyze, then there will be several terms acting on this function. For some terms that act on electronic degrees of freedom, term in Hamiltonian, or Hamiltonian acting on its eigenfunction converts into a number times eigenfunction, so one gets rid of operator. For some, it will be still a quantum operator. And then we will take a decision which terms to keep, which terms to drop, and we will get deeper into Born-Oppenheimer approximation. Yes, looks like we are arriving to the end. And this was answer on questions after the meeting in one of the previous years about how the Schrodinger equation is typically solved. So in all practical computations, people try to depart from dependence on continuous variable and formulate all equations in matrix form, right? It's just a little idea that, again, do not listen, do not focus, we will come over it once again, but all equations, all differential equations that come up here in practical computations, in the codes that computers are solving, they are reformulated from equations as for independent variables into matrix equations. So diagonalizing matrices. So computers that serve us just diagonalize matrices all the time.
So question.
Yes.
On the slide that you had with the wave function, that one. Mm-hmm. So really just understand that formal solution that you have your position of your ions or your index of eigenstate relates back to your Hamilton or to your Schrodinger equation. So relating that back, just understand how those two are connected, and then you'll be pretty good.
Mm-hmm.
Okay, just wanted to relate back. So your wave function is describing your Hamilton. You're describing your system.
So this psi capital describes the whole molecule. Again, I was playing lazy and didn't wrote everything explicitly. But here should be brackets, and it should be the list of all electronic positions and all nuclear positions.
And what are you trying to say in the blue? Like, I'm trying to understand.
Molecular Schrodinger equation.
Okay, so what we saw before.
Yes.
You didn't get that. You didn't get that.
I believe I'm done, but I'll stay here and answer any questions. But I think it's enough for today. I'll check if the tech support installed right software on these computers. If they did, then I will announce the first lab tomorrow. If they will be late, then we will postpone it for 1 week. So stay tuned for announcement from me.
So we'll be doing Gaussian, right?
Gaussian.
Gaussian.
Gaussian for first like 5 weeks, and then was for.
Okay. So we could do it anywhere on campus, or we had to be in chemistry to do that.
We can go into the LED 203
Yeah, I was
as well.
thinking that. unless
But
it's
they
not-
then for some of you who may miss a class, they do not have recording facilities.
I see. Gotcha.
Here it is also not perfect. The meeting that we did on Thursday will be like video, and here it will probably just stuff on the screen. I don't know how much you need the video, but
Well,
definitely for the time when you make the presentations, we need the video.
mhm. Do you kind of feel like the book, the one that one, yeah. Do you feel like it's more like an overview? Because I have Levine, but I have the red book. Or do you feel like this one's like more basic?
There is no single book that will guarantee us happiness.
Okay. Do you have any particular favorite thing about that one?
Let me go off record and then I'll tell something.
Okay.
Or I can just mute microphone. Okay. When it will be something really important, I will just make Xerox of a couple of pages and distribute.
Oh, okay, got it. Okay. Okay, that works.
Okay. More questions 1. More questions 2. More questions 3. Session closed.